Hi everyone, this is going to be a video walkthrough on question 3 on exam prep week 12 for sorting. Okay, exciting. I think this question is really good for testing understanding of these sorting algorithms. Okay, so for each one of these parts, we need to figure out if the statement is true. If so, provide an explanation. If the statement is false, we should provide a counterexample. Perfect. So let's get started. For the first question, it says Quicksort has a worst case runtime of n log n. Okay, where n is the number of elements in the list we're sorting. So Quicksort doesn't have a worst case runtime of n log n, it has a worst case runtime of n squared. So this is false, and a quick reason why is suppose we have the array 5, 4, 3, 2, 1. What we notice is that if 5 is the pivot, right, then the next time we recurse on 4, 3, 2, 1. Then 4 becomes the pivot, and then we recurse on 3, 2, 1. So continuing this pattern, what we'll see is that the first iteration of Quicksort does n work. The second one does n minus 1 work. Okay, and so on, where we get the following sum of n plus n minus 1 plus n minus 2 all the way up till 1, right? And we know that this sum, written a little more cleanly, right, is equal to n squared, right? Or I'll say like not exactly equal, but asymptotically equal, right? So we see this is false. The worst case is not n log n, it's rather it's n squared. Okay, and then this is the counterexample. Okay, nice. So the next question states we have a system running insertion sort and we find that it's completing faster than expected. What can we conclude about the input to the sorting algorithm? Okay, so when we run insertion sort, one way of thinking about its runtime is theta of n plus k. Okay, so theta of n plus k comes from the idea where k is equal to the number of inversions. Okay, so this is another way of thinking of this runtime of insertion sort. And you guys might be saying, hey, Soham, what's an inversion? So an inversion is when we have the pair a comma b, and a is greater than b, but earlier than b in the array. Okay, so let's look at an example and it'll make some more sense. Suppose we have some array where we have like 7, and then we have 3. So we could see that the pair of 7 comma 3 is an inversion because 7 is greater than 3, but earlier than 3 in the array. Okay, and another way of thinking about inversion, it's when two elements are out of place, right? 3 should be before 7, so we can kind of see here that that's an inversion. Okay, so if the runtime of insertion sort is relatively fast, what we can conclude is that k is small, right? If k is small, what we can conclude is that there's not too many inversions. And then what we can finally conclude, if there's not that many inversions in a given array, that means it's nearly sorted, okay? So what does that, like, how did I make that jump? Suppose we have a nearly sorted array. Okay, let's just look at some example here. Okay, so this array is pretty close to sorted, right? And since it's close to sorted, we see there aren't many inversions. The only inversions involve the number 0, right, and 1. That's one inversion. And then we also see some other inversions are 3 and 2 and 4 and 2. Okay, So these are all of the inversions in the array. So we can kind of see here that if there aren't many inversions, it means the array is in nearly sorted order. Okay, so let's move on to the next example. Give a 5-integer array such that it elicits the worst case runtime for insertion sort. Okay, good question. So whenever we think about the worst case runtime of any function, we want to make us do the most amount of work as possible. So if you guys recall how insertion sort works, is that we have a list of numbers. Let's pull up some example. I'm just going to show you guys the solution for simplicity. Okay, so we have some list of numbers, and then each time we go at a given number here, and we keep swapping it to the left, which is hopefully in this direction when this video is mirrored, until it gets to its correct position in the beginning, right? So in order for us to do the most amount of work as possible, we want our swapping operation to be as much work as possible, right? So what that means is every time we're at a given element, we want to move it all the way to the front, right? It should go all the way to the front each time. In order for it to go to the front each time, it must be smaller than everything we've seen so far, right? And we can see an example of that is the array of 5, 4, 3, 1, 5, 4, 3, 2, 1, because when we're at 4, we have to swap 4 and 5. Then when we're at 3, we have to swap 3 to the front. And we see that every time we're at a new element, we have to move it all the way to the front, and we create the worst case behavior. Okay. Nice, cool question. So the next one, heap stored is stable. Okay, so this one is actually false. The intuition for why it's false is because when we perform like heap sort, what we're doing is we first heapify the array. Okay, so and then what we do is we keep removing the minimum. Okay, so what's happening here is that there's a lot that's happening, right? The heapification and the remove min, right? In order for us to preserve stability, we need to ensure that if we have a 5 and a 5, let's say 5a and 5b, then after performing the sorting algorithm, 5a is less than 5b. But in the process of heapifying and in the process of calling remove min, this technically isn't the case. Okay, and in the solutions, there's an example of a potential array that actually elicits this behavior. But intuitively, since there's so much happening here with heapifying and remove min, there's no way that we can ensure stability. That's like how I approached it. So the counterexample is a bit hard to think of. So I recommend just looking at the solutions for that one. Okay, false. See solutions. Okay, so give some reasons as to why someone would use merge sort over quicksort. So this is a good question. So the couple pros merge sort has, I'm just going to go through this one quickly because it's on the solutions, is that it is stable. Okay, it has a better worst case. And it's okay. And since it's stable, it also implies that it's good for objects. So what that means is, suppose we have a bunch of students, okay? So let's say that all of the students are sorted by grade, okay? So we see we have all the students in, actually no, let's do all the students are sorted by grade. So we have all of the A students here, all of the A minus, B, and so on, okay? And what we want to do is we want to sort all of the students by their year in school, okay? So what would happen here is ideally we would have all of the people in 9th grade in the beginning. Well, we would know we would have all of the people in 9th grade and all of the people in 10th grade and so on. But within each grade, it would be really, really cool if they were ordered in terms of their grade. What that means is if we have a student over here, let's say student, I don't know, T, and then we have a student S over here that are both in 9th grade, then in the new array we have, the T is before the S student, okay? The reason is because the T student has a slightly higher grade than the S student, okay? So stability ensures that this happens because when we sort on grade, technically T9, T, who's in 9th grade, and S, who's in 9th grade, have the same grade. But if it's stable, we know that we promote or we preserve the previous ordering by grade. So, or by grade in the class. So then when we go here and we sort by year, I realized grade's kind of confusing. That's my bad. Let's make the second one year. Right, but now by setting on year, we preserve the grade ordering we had before. Okay, it's a quick tangent on stability and why it's good for objects. Okay, so this last question is fairly tricky. And I'm guessing if you guys are watching this video, you guys might just like fast forward to here, which is totally fine. Okay, so you'll be given an answer bank and we need to figure out for these questions, list all from above that apply. Okay, so something that's bounded by an n log n lower bound. Okay, so something that has an n log n lower bound, well, let's see here. What an n log n lower bound means is that this is the same as saying we cannot do better than n log n. Okay, that's like an intuitive way of thinking about a lower bound for a function. Okay, so I'm going to walk through all of these algorithms and I'm going to ask myself, can this algorithm do better than n log n, right? Can Quicksort do better than n log n? It can't do better than n log n. The best Quicksort can do is n log n, right? The reason is how Quicksort works is in its best case, every time we choose a pivot, the pivot uniformly partitions the entire array. And even in this case, the total amount of work that we're doing, this is a bit of a jump, but hopefully you guys catch on. The total amount that we're doing results in this recursive tree where we have n at the top, then n over 2 here, and then we see the total amount of work that we're doing creates this recursive tree of height log n, where we do n work per level, and we do n log n work. So in the best case situation in Quicksort, when we constantly choose the pivot, and we constantly choose the pivot as the median, right, and it partitions the array beautifully, we still see that in its best case behavior, we don't do better than n log n. Okay, so I apologize if this recursive tree didn't make a ton of sense. I'll fill in one more section. Okay, so yeah, this is the recursive tree for Quicksort. If it didn't make too much sense, no worries. But the gist is that each iteration of Quicksort in the best case takes n log n time. Okay, so let's keep going. Merge sort always takes n log n. Okay, selection sort always takes n squared. So with this in mind, we know that both merge sort and selection sort cannot do better than n log n. So here, let's put in A, B, and C. So far, we know that quicksort can do better than n log n, merge sort can do better than n log n, selection sort can do better than n squared, which implies it can do better than n log n because n log n is better than n squared, right? Okay, insertion sort can take us n time if no inversions, or i.e. in sorted order, right? Okay, and then heap sort can also take n time if they are duplicates. Okay, so with this in mind, we see the only three that actually fit are A, B, and C. Okay, let's move on to the next one. For the next one, we see has a worst case runtime that is asymptotically better than Quicksort's worst case runtime. So let's first recall what is Quicksort's worst case runtime. Quicksort's worst case runtime is n squared. Okay, so in order for something to have a better worst case runtime than n squared, its worst case runtime probably will be n log n or better, right? So let's look through these options. Well, obviously not quicksort. Okay, merge sorts is always n squared, or it's always n log n. So we see that this is indeed true. Let's put a green check for now. Okay, selection sort is always n squared, so it's not the case. Insertion sort, worst case will take n squared, so it's not insertion sort. And then we can see here that heap sort will take n log n in the worst case as well. Okay, perfect. So we see here that the only options that suffice are B and E. Okay, moving on to the next one. In the worst case, performs n pairwise swaps of elements. Okay, so what this is saying is that the maximum number of swaps this algorithm will do is n swaps. Okay, so I'm going to go through each of these sorting algorithms and ask myself, is there a possibility that we do more than n swaps? If so, we can't use the sorting algorithm, right? Can Quicksort do more than n swaps? Well, yeah, it can do more than n swaps if whenever we choose like a pivot, like say we have this array, we could maybe choose a pivot, right, that moves all the way to the right, and then every other element like has to go 1 over, right? So we could see here that if the array, let's think of a quick example off the top of my head. Suppose the array was 5, 4, 3, 2, 1. What will happen in Quicksort is that we'll move 5 to the end, and then we'll have to move all of these elements over by 1, right? So in that case, that this was going to take like n minus, it'll take like n swaps the first time, then n minus 1, and then so on. So this will take a ton of swaps. Okay, so not Quicksort. Merge sort also is not going to be the case because it's possible that each time we merge two arrays together in merge sort, each time we merge two arrays, that we constantly swap elements, right? Right, merge sort can cause a lot of swapping. Okay, so it's also not merge sort. Selection sort, interesting. So in selection sort, this indeed is true, that in the worst case, it will take at most n swaps. The reason is that in selection sort, what we're doing is that each time we find the minimum, and then we move the minimum all the way to the front. Well, we can only perform this swap to the front n times, because we can only move the minimum to the front n times, because there's only n elements. So selection sort is true. Insertion sort also isn't the case, which we can look at with input 5, 4, 3, 2, 1. That's a great counterexample. Okay, and then heap sort is a ton of swapping in heap sort, so not the case as well. So the only answer to this one is C. Okay. For the next one, it states it never compares the same two elements twice. I think this one is the trickiest question here, so I'll try to go slowly so it makes sense. Okay. So in Quicksort, do we ever compare the same two elements twice? Well, let's look at some example. Okay, let's just like use a sample array. Suppose that we compare the element 1 to the element 2 more than one times, okay? So the only time we ever compare two elements in Quicksort is if we choose something to be the pivot, and then we compare the given element with the pivot. That's the only time we compare elements in Quicksort, is when we compare an element with the pivot. So the only possibility for us to compare 1 and 2 together multiple times is for us to choose 1 as the pivot, compare 2 to 1, and then choose 2 as the pivot and compare 2 to 1, right? The problem, or the reason that's not the case or would never happen, is that once we choose 1 as the pivot, we solidify 1's location in the final array. What that means is after choosing 1 as the pivot, we never do anything with 1 ever again in the sorting algorithm, right? Because 1, after becoming the pivot, is put in its correct position in the output array. So after comparing 1 to 2, when 1 is the pivot, we don't compare any 1 to 1 ever again. So we know that Quicksort never compares the same two elements. Okay, so looking at merge sort, the only time we ever compare two elements in merge sort is if we're merging two, let's say that we're merging these two sorted arrays with each other, okay? What would happen is that we would compare 1 and 3 when we put 1 in the beginning, right? Then what we do is we compare 2 and 3, right? I'm just performing the merge operation, and then we put 3 and 4 here, okay? So all I did, just to give more light on what I'm doing, is I just merged the 1, 2 with the 3, 4. And why I did that, if it may seem kind of obvious, is that when we merged 1 and 2 with 3 and 4, we only compared 1 to 3 once. And after we merged these 4 elements together, we will never compare 1 with any one of these elements. In the same light, we will never compare 3 to any one of these elements, right? So with that, what we can do is we can conclude the only time we ever compare any two elements together, right? Let's just choose these two arbitrarily, is when we merge their respective arrays together. And since this process only happens once, we know for a fact that merge sort never compares the same two elements. Okay, selection sort can compare the same two elements, and I'll give you guys a quick example. Suppose we have the array 2, 3, let's go 4, 5, 1. What'll happen is that the first pass, we choose 2 as the minimum, and then we compare 2 and 3 together. Then what happens is that we move 1 to the front, right? This is pass 1, this is pass 2, and for the next pass, we swap 1 and 2, right? And then we see here that we compare 3 and 2 together again once 3 becomes the minimum and we compare 2 with 3. So we see here that we've compared 2 and 3 twice. No, okay, so we can eliminate selection sort. Okay, so let's look at insertion sort. How insertion sort works is that we have, let's look at an example. Okay, so the only time we ever compare 7 with anybody else is when we move 7 to the left by swapping it with its neighbor on the left, right? So we can see here, like, pretty safely that we only ever compare 7 and 4 once when we're swapping 7 to the left. After that point, 7 and 4 are never compared again, right? Okay, so with that in mind, we can also conclude that this is a green check. So in heap sort, we can see that it's possible for us to compare the same two elements. It's a little tricky to think of a counterexample, but the intuition why is that heap sort is split into two phases. It's split into heapification, and it's also split into remove min, right? So it's possible that we do a comparison in the first stage, and then we do the same comparison in the second stage, right? Okay, so we can see that it's only A, B, and D. Phew, that was a tough one. Okay, so at the last problem, we see it runs in best case log n time for certain inputs. So this is actually a trick question because nothing can run in log n time because the sorting algorithm has to look at every single element, and we can't look at log n elements to sort something. We have to look at everyone. Okay, thanks for watching. Hope you guys enjoyed it.